In the last video, we looked at how we can use measurements to extract important figures of merit of a waveform off the front screen, but we cautioned against blindly following those measurements. We always want to first apply our Mark 1 eyeball to get a rough estimate of what that figure of merit is. Never blindly use a measurement off the front screen unless you can first evaluate, is it reasonable and does it apply for this particular waveform. But when it does, when we have confidence in the value, measurements can be incredibly powerful to fully characterize a particular signal that we're looking at. And in this video, we're going to look at using the measurement functions in order to completely characterize a square wave. And I've listed here some of those measurements. And we want to be thinking about, when we characterize a signal or a waveform, we want to be thinking about what is the parameter we're looking at? What's that figure of merit relate to? Is it a vertical measurement? Is it a voltage or an amplitude kind of measurement? Or is it a horizontal measurement? Is it a time-related measurement? So these sorts of features of the min and max values, peak to peak and average, RMS, these are all about vertical measurement. These are about voltages of the signal. Anything that relates to a time period is going to be a horizontal measurement. The frequency period, the on and off time, the resulting duty cycle. All of these are going to be related to a time period measurement. Let's take a look at using the waveforms in order to fully characterize a square wave, and that means that we're going to have to generate that square wave from the wave generator. So here's our setup. We've got the scope. We've got the input to channel 1 going to the wave generator. The 1 plus is going to the signal output of the wave generator, and the 1 minus, remember it's a differential input, the 1 minus is going to ground. So we're doing a single-ended measurement. Always important to pay attention to that. That's our setup. Now let's open up the Waveform software and we'll take a look at our signal and we'll generate a nice square wave and we'll characterize it. Here's the software. We're going to turn on the scope and we're going to turn on the wave generator. Let's check the wave generator. We want a square wave. Let's set it up for, we'll do 2 kilohertz, and of course if we wanted 2.5 kilohertz, for example, we just type it in and there it is. We'll use an amplitude of, let's go 1.5 volts. That means it's going to go above 0, 1.5, and below 0, 1.5. We'll add a DC value to it of 0.5, and let's add a little bit of asymmetry to it. Let's make it a 30% duty cycle. So now we've added a little bit of structure to it. And here's what that waveform is going to look like. We're going to turn it on and let it run. Now it's outputting. Let's turn on our scope and let's take a look at that waveform and characterize it. And how do we get the scope window? Remember, we come up here to the welcome. This is where we select all the different instruments that we want to use. We select the scope and here it is. Now we can decide how we want the different windows to display over here. And so let's just do one window at a time. So here is the scope. I don't see anything. How come? Because the scope comes up natively in the stopped mode. It's ready to be triggered. And always check the trigger settings. So we're in auto. Always a good way to start out if we don't know what trigger level to use. The triggering is going to come from the source in channel 1. We're going to look at a rising edge and the trigger level is at 0 volts. Perfectly reasonable. So we're ready to turn on the signal. What do we expect to see before we look at what do we expect? Hey, you know, it's going to be roughly an offset square wave with some funny duty cycle. Let's take a look. We run and it's going to be about 2 kilohertz or so, 1.5 kilohertz. And here's that signal. It's distorted a little bit. I have channel 2 on. We're going to look at channel 2 in a little bit because we're going to look at the crosstalk on channel 2. But for now, I'm going to turn channel 2 off. So here is our waveform. It's offset a little bit. It's distorted. Now you can see there's noise on top of this because we have RF pickup. We're going to look at that in a later video as well. I recognize, yeah, there's RF pickup because I have jumper wires. There's very little I can do about that. And we'll see what we can do and how using a 10x probe will dramatically improve that. So because I understand there's noise, let me turn off the noise. So we come over here to the little gear in channel 1. That means settings are here. We click on the settings and we turn the noise off. And there we go. And now let's take a look at our square wave. So we're at 1 millisecond of division. We've got 1 cycle, 2 cycles, and a little bit more. So it's a little bit more than 2 cycles per division. So it's about 2 kilohertz as the frequency. The duty cycle we can see here, a little distorted. So we have a rough idea of what to expect in the signal. Our offset, where's it's the DC offset is the DC average. That's not quite the same as the offset. And so we're going to have to, the offset is going to be where is the midpoint between the high and the low. It's not the same as the average value. So let's use measurements in order to extract some of these figures of merit that describe this square wave. And how do we do measurements? That's going to be in the row of tools right above the trigger. And let's see, we want measurements. Here it is, measurements. We open it up, and now we're going to add. And we're just going to use the measurements that are built in and already predefined. We're going to look at the channel 1 input. Let's look at the vertical ones first. What do we want to describe? Well, and again, there is a min and max versus average. The average is not the same as the DC offset. Let's see, we'll take the max, we'll take the min. That would, if there was overshoot, that would include the overshoot. We'll take the average, and that's going to be the DC average. Let's see, we'll take the peak to peak. Let's see, we'll take let's do the RMS. The difference between AC and DC RMS is that AC RMS does not include the average in the calculation. So let's take the average RMS. Let's see, and that's a good selection for the vertical measurements. Let's take a look at the horizontal measurements. What do we want to include? We'll do the frequency. The period, of course, is just 1 over the frequency, but sometimes it's useful to see both numbers. The duty cycle. I like the positive duty cycle that tells us what percentage of the time do we have a high. Let's see, negative, the positive width and the negative width. Let's do the rise time and the fall time, recognizing that whenever we look at rise and fall time, we always want to be thinking about our resolution, because we're only sampling at 800 kilosamples a second. That means, roughly about every 1.2 microseconds we're taking a measurement. So don't expect to see a rise time shorter than about 1 or 2 microseconds, because we just don't have that resolution right now. This is part of situational awareness, being aware of the limitations of the measurement compared to the signal itself. Okay, we've selected a lot of different measurements. We say add. They're in there. So I might have clicked add twice for the rise time. So let me take one of the rise times out. So we're going to remove that, or the fall time out. So let's see, how good a job did I do? Okay, I got a whole bunch of them in here. They're all giving us measurements. Every cycle, every time we do a measurement, every time we do a buffer acquisition, we're going to be doing a measurement. They're going to fluctuate, and so I like to add the average value. So we're going to, under show, we click average, and now we've got a good selection. And every time I want to reset the average, I just push the reset button here, and it starts averaging all over again. Now, maybe I'd like to expand the scale a little bit, just so I can visualize it a little bit better. The data's still there. Whatever we take in that buffer of 8,000 measurements, that's what these calculations are being performed on. Let's expand it out just a little bit. Now I can see that waveform a little better. And we're going to take this buffer, do the calculations, take another buffer of data, do the calculations, take another buffer of data, do the calculations. Let's take a quick look at what the numbers are. Okay, the max is 2. Yep, that's about it. The min is 1. I got a little bit of overshoot here and overshoot here. And so that's why it's not exact, because it's max, not the high or the low, which would be the average. The average itself is, let's see, where's the average? It's about 100 millivolts, so that's over here. And it's really hard to do that in our head unless it's a symmetrical waveform. Let's see, peak to peak, yep, there it is. It's the min minus the max minus the min. It's a little bit more than 3 volts. Now the frequency, yeah, 2.5 kilohertz. That's exactly what we expected. That's what we put in, roughly estimated 1 over that, 400 microseconds. Well, we're not at 30%. We're at 29.98% duty cycle. So again, pretty darn good compared to what we put in. The positive width, the negative width, and here's the rise time. Now remember, our sample rate here is 4. We changed the scale. We're at 4 megasamples a second. That means every 250 nanoseconds we're taking a measure. Don't expect to be able to measure a rise time any less than about 200 to 400 nanoseconds. And what have we got here? We got 0.5 microseconds, or 500 nanoseconds. So I could believe this is at the instrument limit. Now let's make some changes in the waveform and see the result of those measurements. So to do that, instead of flipping back and forth between the waveform generator and the scope, let's put them on the same screen. That's where we come over here and we change the windows. We dock one under the other, and I don't need this to be very big, so I'm going to make the top window bigger. So let's see, if I change the frequency, so we're at 2.5 kilohertz. Hey, let's go up to 5 kilohertz. So we can just select that, and we went to 5 kilohertz. But wait a minute, that's not 5 kilohertz. Yeah, we're measuring each buffer value 5 kilohertz, but the average isn't that. Again, situational awareness. We're doing a running average. If we want to get the average after we've made a change, that's where reset comes in. Yep, there it is. Let's see. Suppose that I make the amplitude much smaller. Let's just do a 0.5 volt. Yep, it changed over here, and min and max changed, the average value changed. But again, I need to reset the averages. I made a change, and you notice, gosh, it's not stable anymore. I'm taking a buffer, I'm taking a measurement, I'm doing the calculations still, but the waveform is moving around. How come? That's because I'm on auto, which is good. I'll see it even if I don't get a valid trigger signal. I'm not triggering it based on the voltage of the waveform coming in and the pattern. I'm triggering it because of time. I don't have a trigger signal coming in, so I just trigger anyway. That's because my level went slightly below where the trigger level is. I need to adjust the trigger level, and now we're triggering. And so if we make a change down here, we'll do another symmetry change. We'll go to 20%, make it a narrower pulse. There we are. And again, we'll reset the averages, and let's see what happened to our positive duty cycle. And there it is, 20%. And so we see how powerful measurements are. If we have a waveform that matches a pattern, an established waveform that we understand, that has certain patterns to it, and we can define those figures of merit based on that pattern, and if that waveform adequately matches that pattern we're expecting, we can use the built-in functions in the measurements in order to extract those figures of merit and instantly get an idea, a quantitative measure of the properties of that waveform. That's the power of measurements. But there's also, with great power comes great risk, and that risk is misinterpreting the results. It's so easy to get a measurement off the front screen. We always want to use our Mark 1 eyeball and test the consistency. How well does that measurement really extract an important figure of merit of that waveform, and what might be an artifact of the measurement?